Okay, so let me just see here. We are in section 4.4 now, coordinate systems. Coordinate systems. So they mention here at the beginning, okay, an important, well, let me just highlight this and highlight this. So an important reason for specifying a basis, script B, for a vector space is to impose a coordinate system on the space. So you're used to, what you're used to is in three-dimensional space is the IJK coordinate system. Okay, the IJK coordinate system. But it doesn't have to be the only coordinate system. Okay, in other words, I think that this is probably worth pointing out here. Okay, so this isn't perfect, but X, Y, Z axis, okay, and okay, we have vectors I, J, and K. How many have seen those vectors in another class, maybe a physics class or an engineering class for three-dimensional space? Okay, Mikhail has, Yasin has, Jacob has. Yeah, and this is a basis. This is a basis for three-dimensional space. And you use it as a coordinate system. So like for instance, if you have the coordinates, say -3, 2, and 7, that means -3i plus 2j plus 7k. Okay, so the coordinates -3, 2, and 7 are the coefficients of your basis vectors. They're the coefficients of your basis vectors. Okay, so like if this is your vector x, we write it as a linear combination of the basis vectors, and the coordinates are the coefficient of the basis vectors. So this is something you're very familiar with. You're very familiar with it. And in fact, that you've used what's called the unique representation theorem. If you have a set of vectors that's a basis for a vector space, then no matter what the vector is in the vector space, there's a unique set of scalars such that that vector can be written as a linear combination of the basis vectors. So like 2, 3, 7, or well, -2, 3, 7 is equal to, those coordinates are unique to that, well, those are unique, right? And if you had a different point in three-dimensional space, it would as a different linear combination of the I, J, and K. But we can be very general in this. We can be very general in terms of taking any vector and writing it in terms of its basis. And the coefficients C1, the scalars C1 up to Cn, those are your coordinates. Those are called your coordinates. Okay, so hold on here. Let me go down a little bit. Okay, so here now, another definition is if you have a basis for a vector space and x is in the vector space, the coordinates of the vector x relative to the basis b are those weights such that x is the linear combination of the vectors. And we call the set of coordinates the coordinate vector of x relative to the basis b. That's what we call the coordinate vector. Okay, so in other words, this here, I just want to highlight it. This is what I'm talking about right here. Okay, this is what I'm talking about right here. So I think it would be helpful to see an example of how this works. So let's go to the notes and let's look at a problem here. Okay, let me let you copy this problem down. Okay, I'll give you a moment to copy that example down. Yes, I think we do have an error here. Hold on. Right here, blow this up. This here should be b sub 2. Thank you for catching that, Mikhail. This is b sub 2. Excellent. Okay, so you have a basis for r squared. Now, b1 and b2 are there. b1 is 1, 0. b2 is 1, 1, 2. What you're used to, of course, is this. You're used to what? 1, 0 and 0, 1. That would be the standard basis that you're used to, but it's not the only basis for two-dimensional space. We could say, I mean, you grew up with this. You grew up with that standard basis. But we could just as easily use this basis, where b1 is 1, 0 and b2 is 1, 2. Those vectors. Let's say you have a vector 1, 6. Well, we want to write the vector 1, 6. We want to know what the coordinates are of that vector 1, 6 relative to the basis consisting of vectors b1 and b2. Okay, that's what we want. In other words, what we want to do here is we want to find the coordinate vector of x relative to basis b. That's what we want to find. If incidentally, just as a little note here, if we were looking for the coordinate vector of x relative to the basis e1, e2, where well, we'll see, Mikhail, where, you know, e1, of course, is 1, 0, and e2 is, of course, 0, 1. Okay. What would the coordinate vector be? What numbers are going to go there? That's right. Good, Mikhail. 1, 6. And that's what you're used to. That's what you're used to. You know what in the XY plane what 1, 6 means. It means you go 1 unit to the right, 1 unit to the right. So 1, 6 means from the origin you go 1 unit to the right. That's what this is. And then you go 6 units up. That's 6 of these vectors, 0, 1 vectors, right? So, okay, but now we got this new basis. So what we have to do is the following. What we need to do is we need to find C1 and C2 such that C1 times B1 plus C2 times B2 equals the vector X. And to answer that question means solving then an augmented system of equations. Very easy to solve. I'm going to take 1/2 times the second row, replace the second row with that result. And then to get the 0 here, I'm going to take -1 times the second row, add it to the first row, put the result there. Yeah, well, you know, but you don't have to use, yeah, it's easy to do. Easy to do. I mean, that was quicker than putting it in MATLAB, right? That was quicker than putting it in MATLAB. So we end up getting C1 equals -2 and C2 equals 3. We end up getting those values. And so the coordinate vector of X relative to the basis B is -2, 3. Okay, that's what it is. Okay, let me know if you have any questions. Now this problem relates to example, well, it relates to, they have a section on graphical interpretation of coordinates, and I'll bring it up. I'll bring it up here if everybody's good with this. You know, what does this mean geometrically? Well, if we go to the book here, how many remember, I don't know, you probably haven't seen this kind of thing, but so figure one and figure 2 relate to the example we just have. So they have the vector, X, which is 1, 6. And of course, the coordinates 1 and 6 give the location of X relative to the standard basis. And that's what you see in figure 1. Okay, so in figure 1, that's the standard graph paper, quadrilled graph paper that you're used to seeing. So the vector x is there, and from the origin, if you move 1 unit to the right and 6 units up, you get to the vector x. But let's say you were to use a different graph paper. In figure 2, they talk about the script B basis graph paper, and they show their vectors B1 and B2. Well, what's B1 equal to? In figure 2, what's B1 equal to? The vector B1. What coordinates does B1 have? So in figure 2, there's the origin, and they've drawn two vectors. They've drawn a vector B1, and they've drawn a vector B2. So what's the coordinate for B1 there? All right. I'll tell you what, I actually have this written. I'll show you here. I have it on paper. I was trying to maybe save a little time, but let's go back to what we had here. So the coordinate vector of the basis B is -2, 3. What does that mean geometrically? Here's what it means. Here's a little picture. Okay, so the basis vectors in the picture are not E1, E2. They're B1 and B2. So B1 here has coordinate, let me see, hold on. Got to write kind of small. That has coordinate 1, 0. And B2 has coordinate 1, 2. Here's the vector x with coordinate 1, 6. So we learned that the coordinate vector of x relative to basis script B is equal to, we learned it was equal to -2, 3. Right? So let me ask you this. You see here how for B2, I have this dot, and this dot. From the origin, if I get up to this dot here, I've moved 3 units with respect to what vector? When I'm here, I've moved 3 units. Oh, wait, hold on. What happened there? Whoa, whoa, whoa. What happened there? Hold on. What happened? Hold on. I don't know what that's about. Hold on. I don't know what happened, class. I don't know what happened here. Hold on. You don't see any change? All right, hold on. I'm seeing, everything looks fine to you? Okay, I'm seeing, hold on, let me just go back. Let me bring it back here. I must have hit a button, a bad button. There we go. That's better from my end. Come on, go down, go down. All right, so what I'm trying to say is at this dot, see, it's not showing up right. It's not showing up right. I'm sorry. Hold on. I hit something and I'm having trouble with this. All right. You see, probably see a big square, don't you? All right, hold on. I'm going to take care of that. There we go. Let's try this again. Give me some love, Blackboard. Give me some love. Thank you, Cameron. Give me some love here. All right. So, yeah, I saw a square too. I hear you. So, here's a dot. Here's a dot. Here's a dot. How many units did I move? How many units did I move? 3 units. Good, Mikhail. With respect to what vector? B1 or B2? B2. B2. You see, Bellin, if you look at the vector B2, I'm moving 3 units. I'm moving like 3 B2 vectors forward. It's like moving 3 units in the B2 vector direction. But then what do I do there? I go here and then here. So I'm moving 2 units to the left with respect to what vector direction? Would be the B1. So what I'm trying to say here, what we learned, right? What we learned is that the coordinate vector of x relative to the basis b is -2, 3. And if we look at the picture, here, to get to this vector x, okay, to get that vector x, which has coordinates 1, 6, I had to move 3 units in the 3 B2 units and -2 B1 units from the origin. Does that make sense? Is this graph helping? Is this helping? Are there any questions on that? Cameron's okay with it? You see, you're used to moving to the left and to the left a number of units on the x-axis and then moving upward or downward. You're used to moving left or right. To plot a point in 2-dimensional space, you're used to moving first from the origin to the left or to the right, okay? A number of units. Those are the E1 units. And then you're used to moving up or down a number of units. Those are the E2 units. But if our basis consists of vectors B1 and B2, then to reach the point, the vector x at 1, 6, you have to move 3 units in the 3 B2 units and then -2 B1 units to reach the vector x. That's what they're getting at here. Okay? And so you see what you can do is you can say, well, if I'm going to use a different basis here, I'm going to need new graph paper. I can't use the standard graph paper in figure 1. I have to use this graph paper in figure 2. That where my units are B1 and B2 units. You see that? That's what I'm trying to get at. That's what I'm trying to get at. Okay, and incidentally, we can go a little further here. We can go a little further with the example. In terms of notation, we can think of the vector x here. We can think of the vector x as a matrix times the coordinate vector of x relative to the basis b. Okay, in other words, this here, this linear combination, okay, of vectors b1 and b2, okay, that can be thought of as, well, you can write a matrix equation. The matrix equation is this: x equals P sub b times the coordinate vector of x relative to basis b. The P sub b matrix is called the change of coordinates matrix from base b to the standard basis. It allows you to take a vector x, 1, 6, which is coordinates relative to the standard basis, and express it in terms of coordinates that go with the new basis. Okay, that's called a change of coordinates matrix. So section 4.4 is actually pretty straightforward to understand, but I think it's good you're seeing naturally some of this, some of these notations and so forth. The change of coordinate matrix from basis b to the standard basis, which is P sub b, transforms a coordinate vector x relative to the basis b. Okay, it transforms it into the vector x. So it's like you go back and forth between coordinate systems, back and forth. Anytime you're given a vector x without any statement regarding to what basis you're using, you assume it's the standard basis. So that would be I, j vectors, or I, j, k vectors. Okay. I want to show you one more thing here, real quick, one more thing, and then I'm going to let you go because it is time. One more thing here from the book that I wanted to show you. It was example. They talk about, incidentally, in the book how you have different crystal lattices, and based on the crystal lattice, a different basis is more convenient than another basis. Okay, so that's fine. But they talk here in example 5. Hold on, it was example 5 that I want. Hold on. Okay, coordinate map, that's fine. Yeah. Okay. So example 5 says, let script B be the standard basis of the space of P3 of polynomials. So those would be polynomials of degree 3. So if your basis consists of 1 comma t squared comma t cubed, you can express any polynomial in P3 space as a linear combination of those basis vectors, 1 t squared t cubed. And so you see the coordinate vector of x relative to that the coordinate vector of the polynomial relative to that basis p is just the a0, a1, a2, a3. How many notice that to determine a polynomial uniquely, all you need to know are the constant a sub 0 and the coefficients of t squared, and t cubed for a third degree polynomial? How many have noticed that? You probably noticed it from in pre-calculus, right? And incidentally, one another comment here I should make is that you can have what's called an isomorphism. So to uniquely determine a polynomial in three-dimensional, to uniquely determine a third degree polynomial, you need 4 numbers. So any third degree polynomial, you can match it with a coordinate in 4-dimensional space because you need 4 numbers to uniquely determine the polynomial. That's called an isomorphism if it's a 1-to-1 onto mapping. Okay, so that's another term that you're going to see in your homework. Okay, are there any questions at all regarding example 5 or regarding section 4.4? Okay, Cameron's good. Okay, wonderful. Well, I will stop the recording then. Thank you.